next up is Mukund Rangamani, who will give us the second installment of AdS here.
Okay, so I'll continue from where I left off yesterday, which was sort of trying to motivate for you how the AdS CFT correspondence arises in string theory, and we'll see how far we go. But my plan today is to give you a heuristic derivation following Malvicina's original argument for the AdS CFT correspondence, why the two sides of the duality, i.e. string theory on this AdS pi cross S phi space, and this rather interesting field theory which you've heard something about from Kostya, n equals 4 super Yang-Mills, are related. Having done that, I'll sort of spend some time discussing sort of the geometry of AdS space today, and give you a little bit of the dictionary between the two sides of the correspondence, how observables on one side are related to observables on the other side. Okay, so let's go back to our picture yesterday. Of type 2b string in flat space in the background of some number, I'll call it n for obvious reasons, D3 branes. So we said that we have these D3 branes sitting somewhere, and they're sitting basically on top of each other. And if you look at type 2b strings in the background of these branes, we can sort of play the usual rules of string theory and ask what kind of excitations we have in the system. And the excitations are basically two kinds. There are closed strings which live in the ambient 10 dimensions, and the closed string spectrum includes gravitons, the dilaton, the axionic field of type 2b, the two-form potential coming from the Neveu-Schwarz sector, and then in the Ramond sector I have a two-form and a four-form, and the four-form has a self-dual field strength. Okay, so these are differential forms. The field strength here is a three-dimensional object. This has a three-dimensional field strength, and this guy has a five-dimensional field strength, which is required to be self-dual in 10 dimensions. On the branes itself, we have some open strings which are confined to live on the branes because the open string endpoints have to be stuck to the branes, and the open string spectrum contains gauge fields, some scalars, and so far I'm just writing out for you what the bosonic fields are. Each of these is appropriately supersymmetrized, and in particular, if we put all of this together, we find that the system has an action which I schematically represent in three pieces: the part that's confined to the brane, the part that's sort of the closed string part, and then the part that corresponds to the interactions of the closed strings with the open strings. The part that's confined to the brane is at low energies is SUN super Yang-Mills with 4-dimensional supersymmetry and maximal supersymmetry in 4 dimensions. This is this n equals 4 super Yang-Mills sphere. The closed string part has gravity, and the interactions just describe how the gauge fields interact with gravity. What the game we are going to play right now is to start with the system and get rid of these 2 bits. We're going to define a consistent decoupling limit where we zoom in to just the degrees of freedom on the d branes. So that limit corresponds in the bulk to a very simple thing. So everything interacts, of course, gravitationally, and gravitational interactions are set by Newton's constant in 10 dimensions. So if I want to decouple the physics on the brane, I just need to switch off Newton's constant. Okay? So if I send Newton's constant to 0, then the gravitational interactions no longer talk to the brane. And if I further take a low energy limit, I focus just on n equals 4 super Yang-Mills. So of course, this is a well-defined quantum field theory in 4 dimensions. As Costa just mentioned, it's a conformal field theory with a parameter. The 't coupling in this case does not run. Okay, so this is one picture which is sort of completely the standard string theory picture of branes interacting with closed strings. Now what we are going to do is replace this picture by a completely equivalent but different description. And the description I'm going to use is the following. As I just argued, everything interacts gravitationally. So if I put some number of branes in some bulk spacetime, I can allow the branes to backreact. They will backreact on the geometry and curve spacetime. So I can write down a curved space geometry which carries the same quantum numbers as the d3 brane. In the only quantum numbers in this setup I have, macroscopic quantum numbers, are those corresponding to the charge of the nd3 branes. So if I write down the corresponding geometry, we can study the physics of this system equivalently in the geometry where the branes have backreacted and disappeared into a geometric description. Okay? So they form a complicated geometry which is called a black brane geometry, and in this case the black is a bit of a misnomer because we will see why, but it's very easy to figure out what is the 10-dimensional spacetime that carries the macroscopic quantum numbers. So let me write out the solution for you. And now give you a picture of the coordinates I'm using. So x mu are the coordinates on the d3 brane. The 3 brane spans a 4-dimensional world volume, so x mu run from 0 to 3, time and 3 spatial coordinates of the brane. R denotes the radial distance away from the brain in the transverse space, which is an R6, which I have written as a phi sphere and the radial coordinate r. So around this at every point is in S phi. What you should think of this geometry as is as follows. The branes in type 2b string theory are a source of gravity and a source of this four-form potential. Those are the only two fields of type 2b supergravity that this brane system sources. So this geometry is a solution of type 2b equations of motion, where geometry has been modified, the gravitons have been sourced, and that is a non-trivial phi form which I'll write as follows. It's dH inverse, so it's the wedge product of the directions on the brane, wedge dH inverse plus star of it to make sure that the phi form is explicitly self-dual. In fact, it's a very simple geometry. It's prescribed by one function of the transverse radial coordinate to the D3 branes. And this one function, in fact, is a harmonic function in 6 dimensions. And there's just one parameter r, which we'll see momentarily is related to the number of 3 branes. So how should you think of this geometry? So let me remind you of some analogous geometries that you might have seen in different contexts. So think of a charged black hole in 4 dimensions, a Rice-Nordström black hole. A Rice-Nordström black hole in 4 dimensions, the solutions to Einstein-Maxwell theory, which carries electric charge and sources some coherent gravitational background. And Rice-Nordström black holes, you also probably know, have an extremal limit where the charge is exactly equal to the mass, and the black hole horizon is degenerate. This is an exact analog of that system for not Einstein-Maxwell, but Einstein coupled to a 4-form potential. The fact that there's a 4-form is what gives you the fact that you have 4-dimensional Lorentz invariance. You have an SO3,1 symmetry along the brane world volume, and you have an SO6 invariance coming from the transverse space. Okay? So this solution was known for a long time. In fact, this solution was written down way back in the early 90s. However, what people didn't know, so these black brane solutions were known, but people didn't know how to interpret them in string theory until the mid-90s, when Polchinski realized that there's a natural description of objects called d-branes, which are basically, as defined, just endpoints for open strings, and the d-branes in perturbative string theory back react in geometry to give you these black branes. Okay, as I said, black is a misnomer because this is an extremal black hole. In fact, not only does it have a degenerate horizon in the sense that the temperature of this black hole is 0, the horizon area of this black hole is also 0. However, it's a completely smooth geometry in type 2b string theory, and since I can't resist, let me draw for you the Penrose diagram of this space-time. So this structure continues indefinitely up and down. These null lines on here are the past and future infinity of the asymptotically flat space, and this null line here corresponds to the surface r equals 0. Naively, you think that something's going to go bad at r equals 0, but it's just like any other black hole horizon. Nothing fancy happens. However, in this case, you go through the horizon and you don't encounter a singularity. This geometry is completely regular. There is no singularity anywhere. It's a peculiar property of two geometries that show up in the context of string theory. One is this, and the other, which I'll describe later in the lecture today, is the near horizon, the back-reacted geometry of something called M5 branes in M theory. Contrast this to this is the of course, in drawing this picture, I have suppressed the phi sphere and three of the spatial coordinates in the brane world volume directions. Contrast this to the Penrose diagram of a extreme or Rice-Nordstrom black hole. Where again you have past and future infinity and a horizon, and as you go in through the horizon, you find that you have a time-like singularity. Okay, which I have drawn by this wavy line. And again, this picture also, the maximum analytic continuation of the space-time also runs back and forward, up and down. Okay, so let's look a bit more closely at this space-time geometry and ask what can we identify. So let me leave that picture there, since I will use it. So if you stare at this metric for a moment, you'll see that at large r, this harmonic function tends to 1, and the metric tends to that of flat space in 10 dimensions, which it should, because large r corresponds to going far away from the brane radially, and the branes don't influence the geometry very much as you go much further away from them. There are localized sources in 6 dimensions. So this is like a point particle from the point of view of 6 dimensions, and if you go far away from the point particle, it doesn't do very much. However, as you come closer to the branes, closer to r equals 0, which is where in our original descriptions the branes quote unquote existed, the geometry gets drastically modified. And that is schematically what I've tried representing up here. This is the asymptotically flat region. There's sort of a deformation of the asymptotically flat region, some throat type region, which is sort of the intermediate r. And then there is the small r region, which is for the moment I will quote, is a geometry in 10 dimensions, which is a 5-dimensional anti-de Sitter space across a phi sphere. So in a few seconds, we will see why that is. But what you can see is as r goes to 0, this part, square root of h, goes like 1 over r squared. And that 1 over r squared cancels with an r squared out front in front of the phi sphere. So at least you see obviously the emergence of the S phi of finite size. What you haven't seen yet is why the x coordinate and the r coordinate combine to give you the 5-dimensional AdS, but take my word for it and we'll see that momentarily. Okay. So the goal here is as follows. I have a well-defined prescription on this side to localize myself to the field theory, the low energy physics of the field theory on the d brane. I want to do exactly the same here, and there are a few indications I have of what I need to do. What I need to do is somehow forget about stuff that's not in some sense close to the d brane. So if they're closed strings, if my d brane is here and they're closed strings and in that corner of the room interacting among themselves, I don't want to keep track of those interactions. So what would the closed strings in that corner of the room represent in this picture? They would just represent closed strings that are freely propagating, uninfluenced by the brane, in this asymptotically flat part of the spacetime. So all I need to do, in a sense, and we need to make this precise, is put a barrier and split off this asymptotically flat region from the region which I think is the core of the geometry, the region which is maximally influenced by the presence of the branes. Okay. So how do we do this? So it actually, again, historically, this part was achieved before it was realized what it means from the field theory side. So what people were trying to do once they realized the correspondence between d branes and these black brane geometries in the mid-90s was to try to understand how you can recover sort of the low energy physics, how much correspondence there is between the physics as described in this branes interacting with closed string picture as opposed to physics described by closed strings propagating in this geometry picture. So as an example, let's do the following. Let me take a pulse of some closed string excitation, which I'll call a dilaton wave, and throw it on the brane. So I can do that here. I can do that in string theory. I can pick up, make a wave packet of dilatons and throw it on the brane. So the brane is some sort of object in string theory. What will it do? It will absorb some part of the dilaton pulse, and it will reflect back some part of the dilaton pulse. It will absorb some energy, and since I'm sending in energy in the form of a dilaton pulse, some open strings will get excited, and the rest will get reflected back. Okay, so we know how to do that in string theory, and that calculation can be done precisely in the action I wrote down. So here, and it's completely governed by how S int talks between the degrees of freedom living on the brane and the closed strings. What I will do instead is, instead of doing that calculation, try to sketch the calculation in this back reacted geometry where I have replaced the branes by just the geometry. Okay. So this is easy, and in fact it's a kind of calculation that people have done for many years in general relativity. It's exactly like scattering of a black hole. This is not a black hole with this is a black hole with a degenerate horizon, but the same principles apply. Okay, so you study study the propagation of a dilaton, what would you do? You solve the wave equation for the dilaton in this geometry. So dilaton, the closed string field I have picked, satisfies a minimally coupled massless scalar wave equation, i.e. it just satisfies box phi equals 0, but box calculated in this non-trivial metric. So it's not so hard, so you can take an ansatz for the dilaton profile, and hopefully I will remain consistent between my script phi's and unscripted phi's. So I have exploited the fact that my geometry here has 4-dimensional Lorentz invariance, and there's a phi sphere sitting at every point. So I'm just mode decomposing my dilaton into plane wave modes along the d-brane. So this is just the, and p mu's are just momenta, and yl is just a spherical harmonic on S5. I've just written the angular momentum contour numbers. I'm not going to write down all the full contour numbers describing this mode, but clearly the Casimir or the main mode, the principal contour number L, is sufficient for our purposes. And I can write down with this ansatz, I can plug it into this wave equation and write down the 1-dimensional evolution equation for script phi of r in this geometry. So that's also easy. So leave that. So what do we get? So we get some equation like, okay, so let me quickly remind you that for scalars, box is that where G mu nu with lower indices refers to the metric above. So it's not so hard to calculate that the wave equation okay. So here there's the obvious derivative bit from the radial variation. L times L plus 4 is the minus L times L plus 4 is the eigenvalue coming from the spherical harmonic on the S5, and p squared, which is p mu, is the momentum coming from longitudinal profile. Now, it turns out actually, for rather surprising reasons, this wave function can be so this is just a Schrodinger problem in 1 dimensions. Large r corresponds to the asymptotically flat region, and small r corresponds to the region I've called AdS5 cross S5. Okay. It turns out that this problem can be solved exactly, but that's not going to be necessary for our purposes. what's necessary, what all we care about is to ask, how does this black brain absorb flux of energy incident on it? And for that purpose, all you need to do is analyze what the large R behavior of this wave equation is, and what the small r behavior of the wave equation is, and do an matching to figure out how flux coming in from infinity is absorbed and reflected. So it's a standard problem in quantum mechanics that you can do. And if you work out an absorption cross section here, you find an interesting answer. That it scales like omega cubed, where omega is P0, the energy incident on energy of the wave. So the absorption by the brain goes down with energy. So low energy excitations are not absorbed by the D3 brain in this setup. Pictorially, what really happens is the following. The barrier I was talking about is physically present. So if I sort of start chucking in particles, and very low energy particles find it very hard to penetrate down to this region of the where the brains have back reacted significantly. They sort of come in a little bit and then find that they don't want to go in. So there's a huge potential barrier between the near horizon region and the asymptotically flat region. And this is at the heart of what I'm going to formulate now, the decoupling argument, which tells me that I can indeed, in a consistent fashion, decouple this region of the geometry from the asymptotically flat part of the space-time. I.e., I can implement what I wanted to do in the geometry, the scheme I proposed at the level of this action. Okay? And this calculation pre-existed Maldasena's sort of derivation of AdS CFT correspondence, and in fact motivated him to think that if you can decouple these two regions of the geometry, the picture you should have is that this picture breaks up into two. Let me get rid of this. In the low energy limit, I have flat 10-dimensional space and some region in some caricaturist form, which is AdS phi cross S phi, and these guys just don't talk to each other. Okay? And therefore, you should be able to identify the physics of closed strings in this region with the physics of open strings in living on the D3 brain. So any questions about this? So right now I'll try to formulate the prescription a bit better and give you the decoupling argument and show you explicitly why this region is AdS phi plus S phi. Before I do that, let me finish off one.
Some time ago, you said about non-singularity of this black hole solution. Can you explain why we don't want singularities in space?
So, let me say it this way. It's a particularly special geometry in that if you try to find a maximal analytic continuation in going past the horizon, you can continue the space-time and you find that there is no singularity. There's no place where curvatures blow up.
Okay, but what about the duality? You have Yang-Mills theory and this gravity dual.
Yeah.
And theoretically, any gravity dual will be non-singular.
No. So there will be. So the way I formulate the correspondence, you'll see in a moment that I will talk about a particular state in the Yang-Mills theory, which is dual to this AdS phi cross S phi.
Sure.
And that particular state will be completely non-singular. It will be the vacuum state. So we could consider, on top of that vacuum state, excitations, which would generically, by standard gravitational properties, produce singularities in AdS phi. But they would correspond to excited states, which I'm not deriving for you at the moment. So we could certainly put, and we will do this in maybe not today, but in subsequent.
What is the sign of singularity in the dual picture, in the picture of Yang-Mills theory?
The short answer is we don't really know, and there is a long answer. So ask me later. Sorry, I was going to say one thing before I moved out of here, which was I have to give you what this rather strange quantity R that showed up here is just related to the number of D3 branes. Okay, it's a solution which carries n units of D3 brane charge because I put in n D3 branes, and the normalizations are as follows. The alpha prime is the string tension, which is Ls squared in my conventions, and Gs is the string tension. I'll need that for later purposes, so let me record that for now.
One small question. This potential value.
Yeah.
That would be at about the distance of the radius of the AdS from the center.
Indeed. So in these coordinates, the potential barrier graph here R equals R of order capital R. Okay. So that's where the throat geometry is, where there's non-trivial variation between the AdS part, which is that small r, and sort of the asymptotically flat part, which is that asymptotically large value part.
So, what case would you have a very long throat?
So the very long throat is obtained by sort of zooming in onto a region close to R equals 0. Okay, so if you're going away from the region from R equals 0 to R of order capital R, you're starting to see the fact that there are interactions between the open strings and closed strings. So the low energy limit, which in some sense you can see that here because there's an alpha prime here, which I'm going to send to 0. And I'm going to scale things appropriately to keep just this region. Okay, so now we have all the ingredients to formulate the decoupling limit argument due to Malvicino. And the argument goes as follows. We'll send alpha prime to 0 because we want to send Newton's constant to 0, and Newton's constant or Planck length sending them to 0 is equivalent to sending the string scale to 0. So let me remind you that alpha prime is Ls squared. The 10-dimensional Newton's constant is proportional to g string squared ls to the 8th. Okay. In 10 dimensions, the Newton's constant has dimensions of length to the 8, and this by definition is L plug to the 8th.
This low energy limit,
Mhm.
the gravitational interactions are already weak because this Newton constant is dimension full quantity, and as
Yeah.
far as I remember, it has to be multiplied. It has to be multiplied by energy to the power 8.
Yes.
So do we really need this alpha prime going to 0 limit?
Okay. So if I take a very naive limit, I'll be left with nothing. So if I just what I want to do is take a limit where I sort of focus in onto this region and somehow keep gravity in this region. Okay, that's a non-trivial bit in the decoupling. I don't want to switch off gravity here as well. So in some sense, what I want to do is not just zoom in onto the branes and make them rigid, but once I zoom in, I want to be able to talk about small fluctuations of the branes themselves. So which is why I'm going to formulate it this way. This is the only sensible way I know of, where you zoom in, you keep small fluctuations of the branes, which equivalently correspond to not just keeping AdS phi cross S phi, but allowing interactions on top of, allowing fluctuations in that background. But you're completely right. Since you have a dimension full parameter here, setting energies to 0 would switch off all interactions.
So how can you see that the interactions are present with alpha prime is going to 0?
So the way we are going to see this is that precisely the way we did the large N limit in the field theory. We are going to sending this guy to 0 would be like sending N to infinity in some sense, but we're going to keep lambda fixed.
No, sure.
So okay. So before and now to go back to sort of question of energy scales, let's relate energy scales at some radial position to energy scales measured at infinity in that geometry. So we know that energy measured in the asymptotically flat part undergoes redshift because of the h to the minus half factor in front of dt squared. So local energy measured at any point with respect to the killing field ddt. So I should say that my conventions are that x mu has t and 3 spatial coordinates, which I'll just collectively call x. And in particular, the energy measured at infinity goes to 0 as r goes to 0. Yeah, by just the standard redshift argument. And this sort of comes close to addressing the question that was just asked, which is that how do I keep finite energies in the down the throat? It's just because I have a non-trivial redshift. So what I want to do is to keep finite energies down the throat. I want to keep square root alpha prime times the proper energy fixed as I take alpha prime to 0. And this amounts to, from the asymptotic point of view, putting in all the factors, I'm just working with order of magnitude estimates here. If I want to keep excitations down the throat fixed, which is to keep this scale fixed, I need to take r over alpha prime fixed as I take r to 0, which precisely like in the 2 scaling is sending g n to infinity but keeping g squared n fixed. And we'll see why that is true in a moment. So I'll keep r over alpha prime fixed, and zoom in onto the region of space-time, which is r going to 0. So it's actually convenient and to introduce, to keep this quantity fixed, to introduce a new coordinate u to be, which is just r over alpha prime, so that u is finite, and then do the coordinate transformation, just explicitly replace r by u times alpha prime in that metric and take the limit alpha prime goes to 0. Okay? So what do you get? You get an explicit factor of alpha prime you see something that you already saw before, that you find that the sphere has stabilized to be of fixed size. The sphere whose size was varying as a function of r in the r goes to 0 limit has stabilized to have a fixed size given by this combination. There is an overall factor in this geometry of alpha prime, but we'll see momentarily that this factor will cancel out in any physical calculation. Okay. And this part of the metric is a 5-dimensional anti-de Sitter space written in coordinates which are called Poincare coordinates, because they are coordinates where there is a manifest Lorentz symmetry in 4 dimensions. And here you see two players which will show up, which you've already seen in the context of n equals 4. There is Lorentz symmetry, and you see an SO6 symmetry, which Koster described as the R symmetry group of n equals 4 super Young mills. In fact, this is not the full symmetry group, isometry group of this spacetime. The isometry group of this spacetime is much bigger. So let me push this up. Just as we thought we started with the relativistic quantum field theory, n equals 4 super Young mills, which had Lorentz symmetry in 4 dimensions, and realized by virtue of conformal invariance that it had a much larger bosonic symmetry group. The spacetime in coordinates written here has only manifest Lorentz symmetry, but it also has larger symmetry group. So and exactly is the conformal group SO4, 2. For the AdS5 part, and the S5 part gives you an SO6 symmetry. I'll quickly outline the matching of parameters on the two sides, which I've somewhat indicated yesterday, and then describe to you the geometry of 5-dimensional anti-de Sitter space.
It might be worth mentioning that u is equal to 1 over z.
Yeah, so I'll work out the coordinates in a moment. So I'll write down the different coordinate charts as we go along. So I should mention that there was a phi form here in the parent spacetime before I took this decoupling limit. So what happens to the phi form? Well, basically what the phi form does is there is a fixed size phi sphere in the geometry, and the phi form has a flux through the phi sphere. So in the AdS phi cross S5 metric, integral of S5 over the S5 is fixed, and it's fixed to be the number of D3 branes. So the parameters we have on the supergravity side are the flux and G string and alpha prime. In fact, we have one more parameter which I haven't discussed, which is in this background. I told you at the very beginning that only the metric and the phi form were turned on. There are two zero modes for scalars. The dilaton is arbitrary, you can fix it to any constant value, and the axionic field of type 2b is also a free parameter, you can also fix it to any value you like. So the 2b string has a complex parameter tau, which is the expectation value of the dilaton and made up of the expectation value of dilaton and axion. But the Yang-Mills theory, n equals 4 super Yang-Mills, also has a complex coupling which you are familiar with, which is nothing but the imaginary part is the Yang-Mills coupling constant, and the real part is the theta angle of n equals 4. So this term multiplies f squared, and this term multiplies multiplies the topological term f term. So the Yang-Mills coupling constant squared is the string coupling, the theta parameter is the axion, and by virtue of the formula that I just erased, r to the 4, which is the parameter appearing in the metric, I've replaced alpha prime by ls squared, and you can see that the size of AdS in string units sets the 't Hooft coupling lambda of the field theory. And one over n is like the string coupling in the box. So here we have an explicit realization of the study we began yesterday. We have a large n theory, n equals 4 super Yang-Mills, parameterized by n, the rank of the gauge group, and the 't Hooft coupling lambda. This guy is explicitly dual, i.e. the physics of this is completely captured by the physics of strings in AdS phi cross S phi, where there's only one length scale, which is the size of AdS phi. The two sizes are identical, and the size of AdS phi in string scale sets the value of the 't Hooft coupling, and the string coupling constant, which tells me how strings interact in AdS phi cross S phi, is set by 1 over n. And now comes the part which makes this correspondence exciting and frustrating, which is we wanted to solve the large n theory. We wanted to solve the theory by being able to compute the physics for all values of lambda. The question is, when can I trust the description of the gravitational solution that I've written down?
In the relations you wrote there, you have some 4 pi's. Are we supposed to believe them?
So this is this will be the answer at large lambda. So I think this formula can get corrections.
But your very first one saying that G Yang-Mills squared is equivalent to G string.
Yeah, I don't think you're supposed to trust those 4 pi's. That normalization, I think I don't need to worry about. You're concerned whether G string is actually 4 pi over G Yang-Mills squared?
Yeah, I was just trying to clarify whether you're deliberately ignoring factors of pi's and 2's in your correspondences there. I think you have some factors in unconventional places.
Yes, I have some. I think at the level of this, I think this correspondence should be correct. G Yang-Mills squared should just be G string. There shouldn't be a factor of 4 pi, but I can check. Okay, so in order to be able to work with the gravitational description, I need curvature scales to be large compared to string scale and Planck scale. Okay, so if my curvature scales in my spacetime are getting of orders the string or Planck scale, then I should no longer be talking about gravity, but rather about string theory and including quantum gravity corrections. And it's clear from here what I need. I have an expression for R over Ls, so I need R over Ls much bigger than 1 in order to be able to trust gravity. But this translates in terms of the field theory parameters to lambda much bigger than 1. So the gravitational description in terms of the spacetime that I wrote down is good only for strongly coupled Yang-Mills theory. On contrary, to work with perturbative Yang-Mills theory in the Swift expansion, I want lambda very small. That's the regime we could calculate the planar diagrams that we were mentioning yesterday. So there is a sort of duality here which says that the strongly coupled Yang-Mills theory is well described by gravity, but weakly coupled Yang-Mills theory requires me to solve the full string theory on that background. So the state of play so far is that we don't really know how to solve string theory on that background. One, for a technical reason, which has to do with the presence of this phi form. So we haven't managed to quantize strings on this space-time. So unlike strings in flat space, where you have a free conformal field theory and you can write down the spectrum of strings in AdS phi cross S5, we cannot do it. Not to date. However, this does give you a good way to study strongly coupled Yang-Mills theory, because in the strongly coupled limit, I simply have a geometric description in terms of some supergravity background. So the strongly coupled limit, lambda very large, n very large, of Yang-Mills theory is essentially classical physics in that background. So if I want to study fluctuations away from that limit, I can do quantum fluctuations, but I can do semi-classical physics in that background and learn about strongly coupled Yang-Mills theory. And that's something you will hear much more about during the course of the lectures. Okay, I have 5 minutes. Okay. So what I wanted to do is to give you a description of 5-dimensional anti-de Sitter space, but I think I'll postpone that for tomorrow. Instead, give you a quick overview of various other examples of dualities between field theories and string theories that you can derive following the same sort of logic as we did here with D3 branes. So rather than start with D3 branes in type 2b string theory, I have two other starting points. One can start with what are called M2 branes, which are two spatial dimensional branes in M theory. So the whole volume is 3-dimensional, and it's known that there is a, so in the cases that I'm going to describe, the field theory is much less known than the n equals 4 super Yang-Mills. N equals 4 super Yang-Mills is a nice, well-defined 4-dimensional field theory, and there are lots of things we can talk about. But here, the examples, the field theory is on much firmer footing. We don't understand the field theory, but the AdS CFT correspondence gives us one way to understand the physics in this context. So the field theory here is an SO8 invariant 2+1 superconformal fixed point with 16 supersymmetries or 32 superconformal symmetries, and there's no coupling constant. This theory has only one parameter, a dimensionless parameter, which is n, the number of M2 branes. at very high so the way you can think about this theory is you can start with 2 plus 1 Yang-Mills, which is free in ultraviolet, and super Yang-Mills theory in 2 plus 1 dimensions, and flow to renormalization group flow to the infrared. In the infrared limit, you recover a super conformal fixed point with this R symmetric group. And this is dual to four-dimensional anti-de Sitter space across a 7 sphere. The 7 sphere appears because I need SO8 invariance, and the 4-dimensional anti-de Sitter space shows up because I need a 2 plus 1 dimensional conformal field here. So we'll see the symmetries more manifestly in the next couple of lectures, but you've already seen elements of this in some of the other lectures. The other example, which again we have very little handle on, is you can start with M5 branes in M theory. Again, it also has only one parameter, and there's no coupling constant. This is dual to what's called a 2, 0 super conformal field theory. Sorry, the world volume theory of the M5 branes is a 2, 0 super conformal field theory in 5 plus 1 dimensions. And you can think of this theory as the UV completion of 5 plus 1 dimensional super Yang-Mills theory. So 5 plus 1 super Yang-Mills theory is not renormalizable, but it UV completes to a 6-dimensional theory, which is this. And this is dual to seven-dimensional anti-de Sitter space times the force field. And in both cases, there's a simple relation between the AdS radius. Now, we're talking about M theory, so there's no natural notion of string scale. There's only a 11-dimensional Planck scale. So I'll give you the AdS radius in Planck units in 11 dimensions. And this scales like n to the 1/3 for the M5 brane case, and I think it scales like n to the 2/3 for the M2 brane case. And there are many more examples you can write down. We might discuss one more case later, which is string theory on 3-dimensional anti-de Sitter space, which is dual to a conformal field theory in 2 dimensions. But before we go there, we will first try to flesh out aspects of the correspondence in the case which is best understood, which is n equals 4 super Yang-Mills tomorrow.
Questions? Okay, let's have a well-earned coffee.